So in class 12th, today we will study Gauss theorem, electric flux and application of Gauss theorem. Let's first of all we will learn what is actually flux. The number of field lines passing through any surface, that is called electric flux. So the flux, it is represented by the symbol phi of the field E through the surface S is defined as phi is equal to surface integration of electric field over a surface of dA. These are the vector sign important. You have to apply this. Whenever you are writing this equation, these vector signs are important. The meaning of flux is just the number of field lines passing through the surface. This is the definition of electric flux. So what is electric flux? That the number of field lines passing through the surface called electric flux and defined as the equation of surface integration of E over dA. Now, what is Gauss theorem or Gauss law? We have to learn this definition. This year it has been asked. So what is Gauss theorem? So in simple language we can say the Gauss theorem states that the total electric flux emerging out from the surface is equal to 1 upon epsilon naught times the net charge enclosed by the closed surface or Gaussian surface. So what is written here? The outward flux of the electric field through any closed surface equal to net enclosed charge divided by epsilon naught. What is epsilon naught? It is the permittivity of free space we had discussed in chapter 1. Let's see its expression. So Gauss law, the equation, it is phi is equal to surface integration of E dA, that is equal to Q net. It is Q net or Q enclosed. You have to write Q net, means net charge, divided by epsilon naught. What is S? S is the Gaussian surface. Q enclosed means net charge enclosed. dA is an element of area. Vector dA is in the direction of outward normal. And value of epsilon naught, that is 8.85 into 10 is to power minus 12 in SI unit. Now, how to analyze the electric flux passing through the different surface. Let's see an example. In this example, there is a dipole. It is a negative charge, it is positive charge. Suppose that we have drawn three Gaussian surfaces. This is one, S1, this is S2, this is S3, and this light one, that is S4. So we have to calculate, we have to generalize an equation for the electric flux passing from these surfaces. Let's see. Assume two charges, plus Q and minus Q, find the flux through the surfaces. Remember, the flux is negative if lines are entering the closed surface. If the lines are entering the surface, then the electric flux will be negative. If the lines are emerging out from the surface, then the electric flux is positive. Now, so first we will learn the electric flux passing out from the surface S1. So S1, that is phi 1 is equal to plus Q upon epsilon naught. Surface 2, because electric flux line are getting inside to the surface, that must be a negative side. What is the charge enclosed? That is Q divided by epsilon naught from the Gauss theorem. Now the third surface, this. In this surface, no charge is enclosed. If no charge is enclosed, so Q is 0. So if Q is 0, then electric flux will be 0. Now the fourth surface. What is the net charge enclosed by this surface? Plus Q and minus Q, that is 0. Plus Q and minus Q is equal to 0. So net charge is 0. So net flux will be 0. Very important example, learn it. This type of question may be asked in your paper and competition also. Let's see. Application of Coulomb's law. So first we will learn with the help of Gauss theorem how to obtain the electric field we had obtained in Coulomb's law. Let's see. Suppose that this is the surface, Gaussian surface, charge enclosed, that is plus Q. Let a small section of area over which we have to find out the electric field. This is the radius. So the distance of actually the charge is R from it. Let the surface, this is dA. Now phi is equal to surface integration E dA, that is equal to E, and dA is what? The total surface area of the sphere. What is the total surface area of a sphere? That is 4 pi r square. So we know very well from the Gauss theorem phi is equal to Q upon epsilon naught. So phi is equal to this and phi is equal to this. Both are equalized. So ER will be equal to Q epsilon naught. This will go to denominator, then it will become 4 pi r square. So it is 1 upon 4 pi epsilon naught Q upon r square, which we had studied in first hand. Let's see the second application. Electric field due to an infinite line charge. Like this is infinite line charge, we have to obtain an expression of electric field at this point. See, we have to draw a Gaussian surface. First of all, it is a line charge, so we have to draw a cylinder, which is known as a Gaussian surface. At this point, having a cross section, that is dA, over which we have to find out the electric field. So how to get it? Phi 0, from here, this is the means learning part you may learn, but actual proving starts from here. So phi integration E dA is equal to, that is, what is dA actually? dA is equal to curved surface area. The electric field will pass from the curved surface area, not to these two surfaces, because electric field are parallel to these surfaces, not be counted. Only these electric field will be counted which are perpendicular to the curved surface. So E is equal to, what is the curved surface area? That is 2 pi r L. This is the formula of curved surface area of cylinder. E is equal to phi is equal to E 2 pi r L. Now phi is equal to, that was actual Q upon epsilon naught. So see, phi is equal to E 2 pi r L, or phi is equal to, it is direct the form we have put, but the Gauss law, this means that Q upon epsilon naught, phi is equal to Q upon epsilon naught, where Q is the net charge enclosed by the Gaussian surface. And what is actually Q? Q is equal to lambda L. What is lambda? It is called linear charge density. The formula of lambda is equal to Q upon L. So instead of Q, we can put lambda L. So phi is equal to Q upon epsilon naught, or phi is equal to lambda L upon epsilon naught. Phi L is equal to lambda L upon epsilon naught. Lambda L upon epsilon naught will be equal to E 2 pi r L. So E 2 pi r L is equal to lambda L upon epsilon naught. So we have to find out the value of E. So E is equal to lambda upon 2 pi r into vector sign. It is actually, leave it for a moment. This formula you may have to learn. E is equal to 1 upon 2 pi epsilon naught into lambda upon r. Or you may say 1 upon 4 pi epsilon naught to lambda upon r. It is the vector form. See, the small part means easy way to learn that proving. Long line of charge. Lambda is what? Charge upon length. It is called linear charge density. From the Gauss law, phi is equal to Q upon epsilon naught. So Q will be equal to, from this formula, charge Q is equal to lambda into length. So Q is equal to L into lambda. If you put lambda L here, then phi will be equal to lambda L upon epsilon naught. But we know very well from the definition of flux, phi is equal to EA. So EA. A is what? That is the curved surface area, that is 2 pi rl. Now, so E will be equal to, from this formula, if you put this, the value of phi, that is lambda L upon epsilon naught, then finally you will obtain E is equal to lambda upon 2 pi r epsilon naught. The same proving we have discussed according to the book.